As I said, today's topic is orthogonal time frequency space modulation. Research work has been done in the literature by many people for several years, but this research is new research done by my PhD student Atif Iqbal, and this paper has been accepted recently, just few days back, in ICC 2025 workshop. Okay. So we are going to learn what is this, what is this technique, and what are the objectives for today's lecture, and what methods we use, and what has been done, how it was basically implemented, and some simulations and conclusions. So let's take a few minutes. Let's spend a few minutes on this. This is a new modulation technique. Now, even though the bullet says is developed for 5G communications, but it's not part of the 5G standard. In fact, it's not been embraced by the industry yet. There are many reasons. I believe I mentioned this before, but let's summarize. Whenever a new technique comes up, it takes several years to get standardized, because standardization means by the time you think about standardization, it should be implemented, should be tested thoroughly, and it should be demonstrated that it works properly as expected. Then it will go into standardization. So standardization is the last step. Research will be at least 10 years ahead of the standardization. Okay, but the standardization is its own benefits. The benefits are that it's going to see the real world. Otherwise, if you develop some abstract idea and then if it is not used in the real world, what's the point, right? So it is important that you develop the technique and then also show the use cases and demonstrate that its performance in many ways, and publish so that it gets to the standard. So for example, today you're saying, if you look at 5G standards, who develops the standards? 3GPP, third generation partnership project. And it develops 4G and all generations. It's not 3GPP, not limited to 3G. It covers all generations. So this is not specifically for 5G, but potentially in future you're going to see. And because 3GPP is supporting non-terrestrial networks, this plays an important role. So once again, we are answering these questions. Who cares? Because we are going towards non-terrestrial networking, that's where this new modulation technique finds its applications. Okay? But now, so far, what techniques are being used? What's the competitor? It is OFDM. So OFDM itself is a very beautiful technique. In fact, I really appreciate the use of inverse Fourier transform in the beginning. Now, if you really go through the technique and see, go through the OFDM process or technique, you will really see how intelligent the technique is. Someone who came up with, people who worked on it. Of course, there may not be one person. There are several people who develop such standards or such techniques. The beauty is, to begin with, you divide, you employ multiple subcarriers. Instead of one carrier, we have several subcarriers with small bandwidths, and then they are combined. You are modulating your input using several subcarriers, and then you are combining them using inverse Fourier transform. That is in the transmitter. In the receiver, you do the other way. In the receiver, you are employing Fourier transform to split. So the concept that I really enjoyed is employing inverse Fourier transform in the transmitter and Fourier transform. That thinking process is very ingenious. That's what I wanted to say. So OFDM is very powerful. Now we are saying, oh, OFDM is not so good for satellite communication. So you will understand why. Okay. So as they say, demand, but necessity is the mother of invention, right? So that's how OTFS has developed. And there are, we'll review this, and by end of the 1 hour, first hour, by end of this lecture, you should have an idea about what is this. Okay? And depending on your background, depending on what courses you have taken before, you will be able to understand to a certain level. So the third bullet says the drawback, the disadvantage of OFDM, the powerful technique that is currently being used in 4G, 5G, and potentially it will be there in 6G also, on 5G and beyond. So it doesn't mean that, oh, it's something, it cannot be, we are not going to use it. OFDM is very powerful for terrestrial communications, no problem. In fact, including vehicular communications on the ground, it is useful. But what is observed is, when we move to high speed nodes, like for example satellites, the Doppler shift is higher. As we know, many of us know, Doppler shift, Doppler effect. They say if you observe a train, then we are talking about sound in that case, and then when the vehicle is coming towards you, you see different pitch, and then when the vehicle is going away, you will see a different pitch. So that's a Doppler effect. But there we are talking about sound waves. Here we are talking about electromagnetic waves or RF signals. Same. So it's the basic idea is the same. So it depends on the amount of shift. Now, what do you mean by Doppler shift to begin with? It is while the transmitter is sending a signal at one frequency, by the time you receive, the frequency is shifted. And that shift is a frequency shift, depends on the speed of the vehicle, or more importantly, or more specifically, relative speed of the transmitter and receiver. So it doesn't matter whether the transmitter is moving or receiver is moving, we are looking at the relative speed. So it depends on the relative speed and the frequency. Those are the two factors. Again, one small homework for everyone, all the students is, so look at what is the formula. What is the formula for the Doppler shift? That anybody can do. You don't have to be an expert in communications to understand. And try to understand why this frequency shift, why it is coming, and what does it mean, what is the impact. But when it comes to communications, obviously the transmitter and receiver are supposed to be in the sync. Now, if you are sending a signal at a certain frequency or using a carrier frequency, and then of course the receiver will be tuned to the same carrier frequency. Like, if you transmitted a frequency and you're listening to some other frequency, you won't get it. So the frequency shift causes shift in the received symbol frequency, which means that your receiver is tuned to one frequency, but you're getting something else at some other frequency. Like if you are listening to a radio, if they program in 101.1 FM, but you are tuning to 102 dot something, then you won't get the signal. It's as simple as that. So what happens? Even for current technology or current 4G and 5G standards, frequency shift happens because when you drive in the car, you are moving at a certain speed. And train, for example, when you're traveling in trains, even in maybe planes, of course there is a Doppler shift. But OFDM is already designed for that. And how do they do? OFDM employs something called carrier prefix, cyclic prefix. So that, in fact, once again, I'm just giving the idea of what is the solution, but it doesn't mean that we are not discussing it thoroughly here. So you need to go back and see, so what is cyclic prefix and how does it help you to compensate for the Doppler shift? That's some small homework you can do at home. All right, we talked about two things. So what is Doppler shift? Now, how Doppler shift is handled today in today's wireless communications or cellular communications. And I told you, they use a cyclic prefix. So what exactly is that? How does it help? So you need to answer all those questions. So that is called study. Okay? Study means just don't take everything for granted. If someone says u equal to v equal to v or distance equal to speed times time, you don't have to take for granted. Now, that's what Newton did, right? When Apple fell down, he didn't take it for granted. He wanted to study it. Then the research. That's when you observe something and question, then research comes. Unfortunately, what happens is we only ask when we were kids. We ask why. Don't touch this. We say why. But now we stop asking. As we grow up, we stop asking those questions. But point is, as students, you need to have inquisitive mind. You have to keep up that same inquisitive mind that you had when you were exploring the world as a kid. Same thing you have to continue. Even when we are old, older, like me and Dr. Sai Prakash. Anyway, we said the drawback of OFDM is high mobility or velocity that induces something called inter-carrier interference. So what is intercarrier interference? Again, I'll describe it briefly, but you have to study, you have to learn more. So what is that? We have several carriers. So what is the power? How does OFDM works? I'll show you a small graph. I think it's difficult to just everything in words. A picture is worth 1,000 words. So here, this is the idea of subcarriers. OFDM transmits data symbols in parallel using a set of orthogonal subcarriers. In fact, by the way, another point, orthogonality is such a powerful concept. And think about how it allows us to, we say OFDM orthogonal subcarriers. Because of orthogonality, we are able to split the data into multiple symbols, and we are using one carrier per symbol. It's a beautiful concept. I would like you to, even though, especially if you are learning Fourier transform, or if you're ECU student, you really enjoy this. So you're employing several subcarriers instead of one carrier, and then on each subcarrier you're sending one symbol. And then all this data is, this is called OFDM modulation. All this data is combined, literally added together. So in the air, all this information is traveling together like superimposed data. So once it is superimposed at the receiver, if everything goes well, that means there is no interference or no noise is reasonable, then you are able to decode. Let's assume ideal environment. You are sending all this data over all these subcarriers, multiple subcarriers, and then at the receiver, you get back the combined data, and then you are using Fourier transform or FFT to split. So which means that all the subcarriers are split, and you are extracting the symbols that are coming on each of these carriers. So basically, several waves are coming in, and then on each wave is carrying one symbol. And then, so each wave is like a subcarrier, and the receiver, you are getting all these symbols by splitting. In the demodulation, you are splitting. So, but then what happens? If there is a Doppler shift, what would happen? These frequencies will be shifted, and not uniformly. If everything is shifted uniformly, you don't have a problem. But the problem is each wave, each subcarrier will shift in a different way. So then what would happen? You get into this term. This call. So look at this. Earlier, these signals were orthogonal to each other, but now you lost the orthogonality. How do you see from the picture? How do you see where is a how did you lose orthogonality? Look at this. All these waves are they pass through this x-axis nicely in a synchronous way. So look at this first wave. The green wave is something like this, green subcarrier. Then the other subcarrier also. There are the 0 points. This is where they're all, you can see they're all in sync. That is, this picture is showing you the orthogonality aspect of these multiple carriers. What are these carriers? There are different frequencies. There are different frequencies, like in multiple harmonics. So orthogonality is powerful, and it allows us to combine and split. No error at all. It's all mathematically perfect, accurate. But then, because of the Doppler shift, and the shift is not even uniform, so it causes something called inter-carrier interference. So basically, the frequencies of the waves are shifted, and the shift causes interference. Again, I will stop here. I won't elaborate too much on this, but basically you should understand through these two pictures what exactly you mean by inter-carrier interference. And because of that, you cannot extract, you cannot demodulate properly. So symbols are coming in so far nicely, but Doppler shift caused the shift, and because of the shift, you are not able to split, you're not able to extract the user symbols. So that's a problem. And what do you do? What do we do? What is currently being done? Because OFDM is popular, OFDM is used, and today we are getting calls are all going well. So how do we handle this shift? Because they use something called to compensate that, we are using something called cyclic prefix. Okay, again, I will ask you to investigate and see what is cyclic prefix, how does it handle this inter-carrier interference, or how does it compensate for it. That's your homework.
whenever our different data is traveling at the receiver will also move. But if the movement of the transmitter and receiver is constant, then
what is constant?
Transmitter or receiver whoever is moving, that constant is speed. Then this Doppler shift will come with constant means.
No. Actually, even the shift is constant because of the when you are moving, the distance also is changing, right? So in conceptually you're right in the sense because yeah, you think even though it is constant speed, think about when you look at the relative speed, you need to look at it like a vector speed. When you say speed, actually not only the magnitude but also the direction. So when you look at as you move, the magnitude may be the same, but when you look at the include the direction like a vector, then you will see the distance between the way you measure, especially at the relative distance will be different. It's not going to be distance is changed, but it doesn't move at a constant speed. So basically, look at the vector pointer, because when you include the direction also. Now, for example, let's say you are sitting and I am moving. When I move in particular direction, the distance will be at certain rate. You are going to see the change. But suppose say I am moving directly just backwards, okay, not in the horizontally. So depending on the direction of movement, the distance between you and me is going to see a different rate. So basically, the relative distance may not be constantly changing, it will be changing variably. So there is a variability. That's number one. That's true. That's also true, because it depends on the frequency. That's a good point. Very good point. So each carrier has a different frequency because these are multiple harmonics. So each carrier has a different frequency. Of course, Doppler shift depends on the frequency also. So yeah. So the key thing is OFDM. With OFDM, you can do certain, you can handle you can compensate for it, but the speed is too high. What speeds we are talking about? With on the ground vehicles, probably 100 kilometers an hour is not a big deal. It's okay. But when you talk about the 100 kilometers is what you can expect. About not exactly the same, not exactly 100, but around 100. But when you talk about satellite speeds, 27,000 kilometers per hour. So that's a high speed. Plus, if you think about high frequency and high speed is a disaster. That's what it is. Yeah, it's not so. So OFDM is capable of handling. The compensation technique is there. The cyclic prefix will help, but it's not sufficient for higher speeds. But you will appreciate why we are talking about OTFS, because OTFS, if you design it properly, it is immune to Doppler shift. Again, that's the question I'm going to ask you. I will show you some concept. I'll discuss it to a certain extent, but you should answer this question. If you are interested in OTFS, you should answer this question and convince yourself why this is sort of immune to Doppler shift. So, but of course, it has to be designed. Okay. So that's the idea. So we talked about generally, some ideas about some concepts about OFDM. We learned, and then we talk about what do you mean by intercarrier interference because of the shift. Now let's look a little more. This is about OFDM, but this discussion is leading us towards the new modulation techniques. The question is, why new modulation technique? That's what we are trying to answer. So Doppler compensation is required to deal with the ICI. And detector, this is only one example. Minimum mean square error detector is one detector typically used for OFDM, but there may be other detectors also. What do you mean by detector? To detect or demodulate the symbols or decoding the symbols at the receiver, we need a detector. So that's what he's saying, MMSE. It's very popular. MMSE is very common technique. And then we say OFDM is useful in underspread channel. So take a minute to understand what do you mean. Take a minute to understand what do you mean by underspread. So that refers to, I put a small note here, it refers to channel where the effects of time and frequency dispersion. What do you mean by dispersion again? Delay spread is time domain. Frequency shift is a frequency dispersion. So interestingly, information, even though we work in time domain, but in the background you have to look at time frequency domain. Information is represented in time frequency domain. So it is a two-dimensional information representation. So time shift or time delay will cause time dispersion. We talked about the like delay spread, time delays. Why is that? Because of multipath. Each path will have a different delay, and that delay causes that what you call time spread or delay spread or time dispersion. So that is one thing. So what this saying is OFDM is good as long as this dispersion is small. But if it is large, like especially when high speeds, then that will cause a problem. OFDM is not sufficient enough to deal with that. So look at once again, whenever you see a term, please do pay attention and try to understand what exactly we are referring to. So this is also a little bit of homework. OFDM subcarrier spacing delta F. So what do you mean by that? Each subcarrier has a frequency associated with that. So what is the difference? Subcarrier spacing, the difference between two carriers. Like if you say, for example, let's say F0, F1, or 2F0, 3F0, if those are the carriers, then the spacing will be 2F0 minus F0, which we call spacing. So what he's saying is a compensation technique to deal with ICI is to increase the subcarrier spacing. Now, can you guess what happens when you increase the subcarrier spacing? So we're saying we can handle. What he's saying is to deal with this intercarrier interference, you increase the spacing between the carriers. So that way, even the frequency is shifted, it won't get into the other carrier. So like let's say for example, like you're sitting in an airplane or like here, and you don't have so much of a wiggle room. If you extend your hands, we have experienced that in planes, right? Whenever you sit next to a person and sometimes they want to stretch, then they'll come into our zone, our space. So one option is give more space, but it costs money for us. So in the plane, if you want more spacing, you have to ask for premium economy or business class, then you get more space. So same way, if you increase the spacing, it's fine. Technique is fine, but it costs more money, which means that you can't. If you increase the spacing, then your spectral efficiency is going to suffer. Your data rate is going to suffer. So those are the issues. But it can be handled. So he's saying it would increase the cyclic prefix. So these are connected. When I say on one hand, I'm saying earlier I said cyclic prefix is used, but now I'm saying it is spacing. But these are connected. So your goal is to connect the dots. Okay. As a student, you have to take some time and say, okay, these slides are good, and you had some interpretation here, but you go back and work on those. And that the impact is it would increase the cyclic prefix overhead and reduces the capacity. So what do you mean by capacity? Is the data rate. The capacity is the achievable data rate. Theoretically, it's a theoretical notion, but data rate is a practical manifestation of capacity. So remember, capacity is the maximum achievable data rate. So when I say it reduces capacity, what does it mean? It means that it reduces your data rate. Just like the way I explained, if you want more space, then you have to, it costs. And then number of seats will be less, right? Maybe that's the better way to say. If you increase the spacing, why they are packing, why airlines are packing? Because they can carry more people. But if you say each person's space needs to be increased, then you have less number of, it can only handle less number of capacity is reduced. Same way here also, your data rates will suffer. Okay, so we understood now the background including OFDM and its insufficiency for handling high Doppler shift. So what's the solution? Here you go. And yeah, this is a technique for OFDM because we are going to build OTFS technique on top of OFDM. So once you know how OFDM works, then OTFS also similar, but it works in a different domain. I'll tell you what do you mean by different domain. So this is a OFDM. So those of you who are already familiar with OFDM, you can appreciate this, and otherwise those who are new to OFDM, do learn. It's a very beautiful technique. So so first of all, your data, whether it is, let's assume a single user, single user talking to the phone, and the data comes in serial but is split into parallel stream. So suppose you collect let's say, give me 1 second, I want to give you clearly some sort of, yeah. So let's assume, so this is a n by m. This n stands for n symbols. Basically, from your incoming data stream, you take n symbols, n number of symbols, and that you form a one axis, and then this is called delay domain, delay Doppler domain. Okay. So one is, yeah, like maybe this yeah, one of this. Let's say let's take the middle one. You have n number of symbols and m number of carriers. So let me go back. I wanted to give you a clear picture about what do you mean by this n times m. So n is the number of symbols, m is the number of subcarriers. So n is to do with the time, m is to do with the frequency. So you create something like a grid, like a matrix. You are correct, but what happens, remember, sometimes you have to create a gap. So you leave some of the subcarriers for several things. One is maybe you want to send some pilot symbols for feedback. So you need to have some carriers for testing purposes, like for example pilots. You're familiar with pilot symbols, right? So what happens is you want to know how the channel is behaving. So that requires you to have a feedback. So what do? You leave some subcarriers for testing purposes, channel information. Okay. The other thing is just one reason. I think that is good enough for you to see why we need to have more carriers than actually symbols. In a what you call perfect world, probably should be equal, but you have more carriers than the symbols. Yeah, that's a general. You can that assumption is fine. But in general, yeah, you're right. But your answer is, your question is very valid, and the answer is that you need to use some subcarriers for other things, for control purposes. Okay? Not everything is only data, right? So some carriers are useful for control or also pilot symbols. So basically you employ m point IFFT. So this is what I'm talking about, inverse FFT, inverse Fourier transform. And then what do you do? What is happening here? From time frequency domain, to begin with, OFDM works in time. Your data is in time frequency. So remember I was telling you information representation is not just time domain, even though visually we see only time domain, but actually it works in joint time frequency domain. So initial data is in time frequency domain, and then it is converted into time domain, and then it is converted into, it's basically parallel to, say, something like serial to parallel and parallel to serial, including cyclic prefix. So cyclic prefix also is another reason why you need more carriers. So what is cyclic prefix? Even though you have n number of symbols, you are adding few more gaps. So you don't really send anything, just zeros, just giving a gap, okay, giving some some length of the data is for just for putting zeros. So it's you're padding zeros. Okay, and the purpose is that to allow for the intercarrier interfaces. So you look at these are together. You are extending the time, also frequency, okay? And that they are not exactly the same. How much cyclic prefix you use in time domain and how many additional subcarriers you need, they don't have to be exactly the same. The data part is fine. So data is like a square, and because suppose you want to have 16 symbols in one frame. This is like a frame. Think of like this is like a one frame of data. It includes a number of symbols and then corresponding subcharacters. So that's like a square. But then for allowing you to allow for intercarrier interference, you need to use something like padding. You're doing some, for example, good padding means something like, suppose you are shipping a box, very delicate box. Once I sent a video recorder without proper shipping, it was broken by the time it reached. So you pad things. So when you pad, actually, what you're doing, you are paying for extra weight, something. But I think you understand exactly what is padding. You're asking why. The why question is to allow for it's a guard band that allows you for preventing or accounting for intercarriers, inter-symbol interference and intercarriers. Okay, so basically, to begin with, you have time frequency domain, and it is converted into time domain. And then it is going through a channel. This is actually not a process, just a channel. What he's saying is it's a time varying channel. So keep in mind if it is time invariant, we don't have a problem. But this is generally the assumption is that in real world the channel is time varying channel. This is a transmitter. The receiver you are getting a stream of data and you are converting once again into a parallel stream. That results in once again time frequency domain. So basically whatever you have here is exactly the same if everything is ideal. So this is the general description of OFDM. Start with the time frequency representation, convert it into time domain. It will go through a channel. And then it is when you receive, you remove the padding things, remove the padded bits, and then the data is now in time domain. You employ FFT, convert it into time frequency domain, and then you do some MMSC detect. So this is the simple representation of OFDM. And you can see, we discussed a little bit about, because Sumit asked the question, we talked about why do you need padding? So here is a simple discussion. OFDM symbols. So we are saying the symbols here, which is a two-dimensional grid, we are calling them as actually one frame is called OFDM symbol. One frame, the whole frame of n by m is called OFDM symbol, one symbol. So it consists of several, for example, so if you are employing a QAM or quadrature amplitude modulation, so initially you do the modulation and then put the QAM symbol here. So you already have done whatever modulation scheme you are using, especially like whether it is 16 QAM or 256 QAM, whatever modulation technique, those are the symbols that go into this. So when you talk about OFDM symbol, you mean one frame, one such frame is called one OFDM symbol. Okay, I think again, this in this class, I'm just introducing you to OTFS, and as part of that, we need to know a little bit about OFDM. That's the reason we're discussing this. So take as much as you can grasp for now, but then you can do homework on your own to understand in depth. So you should never leave anything half-cooked. Half-cooked knowledge is more dangerous. So it's important for us to learn anything that you're doing. In fact, I ask my students, if at all you're doing something, why do we have to do it half? Do it full. So anyway, so the point is, we learned about how OFDM transmitter and receiver works in a succinctly. Didn't go into too much detail. Now OTFS, here is that. Now we are ready to see what is OTFS and why it is and why we should care. It is developed by Adani, and he's one of the, if you type Adani and OTFS, you'll see lots of papers. Around 2015, 16, 17, I think. The first papers came at that time, almost 10 years ago. So this work has started almost 10 years ago, but still it hasn't seen the real world. It's useful for high mobility applications, particularly for drones and satellites and high-speed trains, and low power applications are for IoT. IoT also is. It is insensitive to Doppler shift. This word, this sentence is tricky. We're saying, oh, no matter what's the Doppler shift, you're good. It's not that easy. We need to really understand why. What does it mean? Okay? So it's more on the design. Interestingly, actually, I did some work today morning. I'll share that with you. I put some notes so that I can make you a little more interested in the topic. The simple statement of, oh, it's insensitive or immune to Doppler shift has to be understood. It's not enough we say, just see the sentence and leave. And the Doppler shift is causing from high relative speed. And another important thing about OTF is this is one of the metrics, by the way. So we talked about metrics, performance metrics. So one of the performance metric is something called low peak to average power ratio, called PAPR. So OTFS is low PAPR, and which is a good thing. So it has a lot more meaningful, but I want you to just give an idea why OTFS is better. It handles Doppler shift better, and also it has low PAPR. Both of them have to be understood in depth. In this lecture, I'm only pointing out to the making you some interesting points, but you need to really do more investigation on it. So why OTFS? Two answers. It handles Doppler effect better, and it has low PAPR, which is a performance metric.
Doppler shift is actually helping it to overcome ICA.
Overcome what?
Intercarrier interference.
That is true, yeah. Doppler shift is helping.
Actually, it's improving by cancelling that ICA.
Yeah, it is helping. Yeah, it is. I'll give you a little more explanation, but it is, the point is, yes, it is effectively handling the Doppler shift. That means it is trying to eliminate intercarrier interference. Now, how are you implementing OTFS? In fact, in the beginning, there were lots of transforms that were introduced, something called exact transform. So it was more complicated. The mathematics was more complicated to begin with. But over the years, the process has been simplified. There were some, in fact, there were transforms like Wigner transform, Zach transform. Now, it was a bit confusing because these are the transforms that are typically used in other domains like physics, for example. So it was complicated, but over the years, people like some of the people who worked on this area, they significantly reduce the complexity. So now we have a very simple process, elegant process. We don't have to think about all those transforms, but they're working behind, So you can't just remove something, some step in the process, but that means it has been substituted differently, but it's much more simpler processes. So it's saying OTFS can be combined with OFDM. The reason why we need to do that, there's another reason why we need to do that, because I wanted to compare OFDM and OTFS. So when you compare, you cannot have two different processes and then say, oh, this works better than the other. So to compare apples to apples, you need to have the same framework. And just to give an idea, I started this work 4 years ago. And it was interesting, actually. I was working at Air Force Research Labs, and usually when we go there, we propose, okay, this is the work I'm going to do. But then, after going there, my mentor, with whom I'm working, he said, I find this new modulation technique very interesting, and then he showed it to me. That's how I got interested. So this is always, for any research work, there's always some motivation, some trigger. So trigger actually came for me from 4 years ago, 5 years ago by my collaborator at Air Force Research Labs. So I'm really thankful to him because he gave me a new topic, which is very useful, especially for the work we are trying to do. For drone to drone communication, which has been my current focus area, OTFS is very powerful. I'll tell you why. First thing is I was only focusing on Doppler shift, but now there's more than that. OTFS is also useful for joint sensing and communication. It's called integrated sensing and communication. So think about the drone world. All these are, by the way, there are research in progress. We're not that all the work has been done. So typically, when you see several drones in the airspace, what happens? You're seeing a lot of drones nearby. So we need to have an idea about which drones are where. I see a lot of people are paying a lot of attention, especially from the back. So in the airspace, you have a lot of drones, and you need to have an idea of which drone is where. For example, when you are driving, you need to know who is in the next lane, who is in the other lane, left lane or right lane. So that way, when the time comes you to move, you know exactly when to move without hitting the other car. So with that, even for drones also, from safety point of view, every drone has to be aware of its surroundings. That's number one. So how do you do that? You need something called sensing. You need to have sensing. And then when the time comes, especially when you need to communicate with other drone, you have to start communicating. So there are two things. There are two aspects. They have to go in parallel at the same time, simultaneously. One is have a situational awareness by sensing, and also when the time comes to talk to a particular drone, like for example, I want to talk to Sumit, or maybe I want to talk to Dr. Sai Prakash, then I need to focus conversation with one person. But to begin with, you need to have an idea about where each drone is near, each person. So having situational awareness and also identifying one particular drone that you want to talk to, that requires something like joint sensing and communication. So perfectly fit. And we haven't started the work yet. That's something that we're planning to begin. And then because we have already so much of expertise in OTFS implementation, our code is already available, and my student actually spent 1.5 years to implement this. And then I think if you guys are having a conversation in the last row, you're disturbing actually. You can step out. If you are disturbing. It's disturbing, like for my discussion. Yeah. So it's very important to have a situational awareness, and then figure out have a directed communication. So we having built so much of expertise, now we want to apply this for this kind of application. Okay. Now let's look at OTFS. Earlier we talked about OFDM. Now let's focus on OTFS. So this is from Hadani in 2021. So pay attention to this grid first of all. So here, in fact, in 4G and 5G they are also called resource grid. But also in some sense you are saying this information is represented in time domain, time and joint time domain, time domain. So to begin with, the data is not in time frequency, but it's something called delayed Doppler domain. So to begin with, information is gathered in the form of delay Doppler. Okay. So this side is Doppler axis, and this is the delay axis. So in between you are seeing delta f. So I'm saying this is a delay, but where is delta f coming from? So the point is there is a connection between the grid width, the width of each cell in time in Doppler domain and delay domain has a relationship. So what is the relationship here? T equal to 1 over delta f. So this has to be maintained. So what does it mean? First of all, what is T? T is the entire OTFS frame duration, or that NT. So each grid has a the width of T and the height of 1 over m delta f. So pay attention to these numbers. These are precise. I checked, validated few times. These are exact. So here I think let's take this. There are n time slots. Okay. So here also there are n time slots, and the width is 1 over nt. And this length or this width and the height are connected. So here the grid dimension is the length of the height here is 1 over m delta f, and here is 1 over nt. So this has to be maintained. So point is to begin with this delay Doppler domain, delay Doppler representation. It is converted into time frequency domain using something called inverse symplectic fast Fourier transform. So couple of observations. One is, as I told you, this is a simplified version. When the OTFS was started, they were using like physics transforms that are typically employed in physics, like Wigner transform, Zach transform. Of course, they were also used in other subjects. Those are more complicated. But here, the simplified version is start with delayed Doppler domain and then come up with something called symplectic first Fourier transform. So one thing I want to observe when I tell my students, we are not inventing anything. We're just learning. Somebody invented. Somebody worked so hard, putting their whole lifetime. Sometimes, as the other day, I was reading Rappaport's book, and then the book is like said, wealth of knowledge, compacted in one book. All we are doing is only learning. We're not inventing. Somebody invented. Somebody did the hard work, and really, are we doing enough justice? That means we need to. How much work they put together to come to bring the technology to this level, and we are simply, just to learn. We're not putting enough time. So that is fascinating. The motivation is, if you are learning the techniques, if you learn the mathematics and all that, you can do wonders. But if you don't pay attention, if you are doing just I'm here because somebody asked me to come, it doesn't go well. So, but after simplification, we got this transform, and then basically delayed Doppler domain data is converted into time frequency. See how beautifully you're moving from one domain to another domain. And then at the end, you convert back into, you convert there's one more transformation. Then you are applying IFFT. So two transforms are happening. Start with delayed Doppler domain and apply inverse symplectic fast Fourier transform to convert the data into another domain, time frequency. So delay Doppler domain is converted into time frequency, and then using IFFT, you are converting into time delay. So these transforms are so powerful and easy techniques, and this is depicted here. Delay Doppler domain is converted into delay time domain, and then it's converted into delay time channel, delay time domain. Then it is transmitted. At the receiver, you following the reverse. So this is the simplest way to implement. And of course, code is available. It's not about we don't have to do anything from scratch. That is the power of internet. That is the power of all these what you call collaborative or open source technique. So the beauty is all these codes are there, and if you understand really what are the principles, what are the concepts that are developed, and then apply for wonderful applications. Like for example, right now I'm looking forward to use this in the context of satellite communications as well as drone-to-drone communications, and then by doing a good job, by learning all these concepts and developing new solutions, what are we contributing? We're not only contributing to research, but also developing to future of aviation or future applications. It's not so great using to WhatsApp and anybody can do it. A first grader can do. Put your fingers and look at YouTube and all. But contributing the technology is what we are for. We are engineers. We cannot waste time by there's no. I mean, there's a compelling reason for us to work hard and develop new things. Right? We cannot waste time. We cannot idly spend time. It's so important for us to be so serious. And sometimes, of course, you can enjoy. For example, yesterday there was International Students' Day. I thoroughly enjoyed. Very nice. We spent some time. But there is a time for focusing. There's a time for spending entertainment. You can't mix them. Now let's look at the mathematical formulation. Okay, maybe we can take 5-minute break. We will take a break and then. Yeah. So far we had a good discussion on the background. What is OTFS and how it is perform? How is it better than OFDM? And then what goes on in terms of implementation with the transmitter and receiver. And we learned several interesting concepts like time delayed Doppler domain, how it is converted from one domain to another domain using some new techniques like symplectic fast Fourier transform, which is a new term. Okay, so whenever I see something like that, I also go to Google and say what is symplectic waveform, and then once you go deeper, you will actually appreciate the concepts. Let me show you something. I'll show in a few seconds, few minutes. So let's start with what is OTFS modulation and demodulation in terms of the mathematics. So far we only talked about the techniques, and then it's still high level, not into bits and bytes. Now we are, what they say, rubber hits the ground. So how actually you do, and most of you know that. So when you basically it's like a transformation. Okay, you're transforming a signal which is in one domain into another domain, just like a Fourier transform. It doesn't look like some example, something. It looks like similar to a Fourier transform, right? Two-dimensional Fourier transform. But what is happening here is take a look at these variables. The input, this is input and output. Input is x mn, and output is x lk, or we call that the time frequency domain. Initially, where are we beginning? What domain is this? What domain is the input? Just think about it. You don't have to answer, but it is in what domain? Delayed upload domain. It's delayed upload domain. So your input is in delayed upload. More specifically, you already have done the sum modulation, which is QAM, quadrature amplitude modulation is. So your input is converted into QAM symbols, and the QAM symbols are placed in delayed upload domain like a two-dimensional grid. Very quickly, we can go back and see this is what you have. Your data is in delayed upload domain, and each of these grid have QAM symbols. Okay. Yeah. So and then you are using you're converting that into time frequency domain. So delayed upload domain to time frequency domain using a transform called inverse symplectic for fast Fourier transform. So what is symplectic transform? As I said, I took some notes by searching the internet so that I can show you. Maybe I think for making sure we are not disrupting that discussion of the flow of the discussion, let's come back to that later. So first, so this is how it is done. So when you have an equation, you can implement. It's not esoteric anymore. It's like, yeah, when we talked about symplectic Fourier transform, but there is a clear-cut expression for it. Then you can implement. And then what happened? What is the time? What is the frame now? It's the same size. Yeah. So output is in time frequency domain. Output is time frequency domain. Now the next step is it can be time frequency domain data is converted into time delay domain by inverse Fourier transform. So there are two transforms. One is symplectic, inverse symplectic fast Fourier transform, and the next is inverse Fourier transform, IFFT. And again, the reference diagram is this. Give me 1 second. Yeah, this is the domain. So you start with delayed upload domain, and then apply inverse symplectic fast Fourier transform, and that converts from delayed upload to time frequency domain, and then you are using IFFT to get into delayed time domain. So one thing that you need to think about is what are these transforms exactly doing to the data and why we are using. And in fact, if you look at cursory level, you say, why are you using two transforms? Both are FFT. Okay. So you have all those questions, but focus more on the domain, delayed Doppler to time frequency and time delay. So those, of course, you need to do a little more homework to understand things a little better and to answer the questions why and what and how. Those you have to do, but process is only, I'm only explaining the process. So once you do this, demodulation is exactly the reverse. The two steps again. The received symbol is transformed. When you say one, it's not one symbol actually. It's called OTFS. It's like a frame. Same thing with OFDM. We call OFDM symbol, but it's actually a grid. Here also OTFS symbol means it's a grid of several like two-dimensional grid of data. So it is converted into time delay domain, and then from time delay domain to time frequency domain, and from time frequency domain to delayed Doppler domain. So you begin with delayed Doppler, and you're also at the end of the day in the reverse process also you are converting everything into delayed Doppler domain. So there are two transforms. One is Fourier transform or FFT. The second is another Fourier transform is called symplectic fast Fourier transform. So basically, this is ultimately this is the data. So time frequency is a time frequency, and YMN is a delayed Doppler. So I think the process is kind of explained in terms of simple terms, and then we are using the mathematical formulas to explain how exactly it is done. But what I think will appreciate what exactly is symplectic transform and what is the significance. We'll talk about that in a minute. In between, you can model this input-output relationship because as a channel. Obviously, you're inputting to a channel, and then you're getting the output. So basically you need to think about, you can model that like an input-output relationship of the channel. So when you, let's go back for a second and see what exactly, which channel we are referring to. Here. So these are the transforms, and you are sending it out on the channel. So between, yeah, after delayed time domain data, after converting delayed Doppler to delayed time domain, you are trending on the channel, and the receiver you are exactly doing the other way. But when you say a channel between this point to this point, that could be modeled as a input-output relationship. Basically, here the channel, we call that as OTFS channel for a reason, or you can say delayed Doppler channel if you want to say. But basically we are referring that when you say channel, you are referring to after you send out from transmitter to until it comes back to the receiver, we are describing that as a channel. So that could be described, that could be modeled as a input-output relationship. So I think that description is good enough. So what is the OTFS channel model? It is showing it's showing a relationship between input and output, and that could be modeled as an impulse response of the channel. For any system, we'll say it's an impulse response. So how do you describe that? The variables are two. One is delay, and the second is Doppler. So this symbol represents delay, and this is Doppler. So this is H is the channel gain, or when you say I equal to 1 to P, there are P number of taps. So this is like a filter. Basically, channel model means you're describing the channel as an impulse response, and in other words, you're describing a system that has an impulse response corresponding to all these taps. It's like a filter, or you can say it's a convolution, or a system that has an input-output relationship, or that system that has an impulse response of this nature. So we are all familiar with this, nothing new actually. So basically we are describing the channel model as an impulse response of a time varying channel. So keep in mind it's a time varying channel. So there are two components here. One is the tau I represents tau I and let's call it nu, tau and nu. Tau I and nu I represent the delay, that means time shift, and Doppler shift corresponding to ith path. So how many paths are there? P number of paths. There are P number of paths, and each path is described in terms of the path, the gain Hi, and tau I, and nu I. So there are three terms corresponding to, what are these paths, by the way? These paths are, remember we talked about multipath before, so you're talking about those multiple paths. How many paths we are accounting? P. How do you know how many, what is P? It depends on your channel model. So we are only modeling, but we don't know exactly how many P, how many paths are there. But you know very well that those paths are nothing but those line of sight and non-line of sight paths. So we already talked about that multipath propagation, right? Multipath scenario. So where one path is direct path, line of sight. And probably, you can assume that tau I is so small for that. If direct line of sight is the shortest path, right? So tau I is extremely small, maybe close to 0. Doppler shift also probably, well, that depends on the speed of the vehicle, relative speed. But maybe practically, maybe close to 0, but you can assume that it's non-zero, something very small for a line of sight. But there are a lot of non-line of sight. So one of them is direct line of sight, the others are non-line of sight. So can you appreciate, I hope you appreciate this simplistic view of this time varying channel, what we are calling as OTFS channel, is nothing but it can be described as an impulse response. And that impulse response consists of P paths. In other words, you can say there are this filter consists of P taps. And remember the taps. When I say tap, A filter is described in terms of number of taps. That's what I'm referring to. But in other words, you can also say there are p paths. Each path is going through different what you call propagation, and hi, this I subscript corresponds to the path. There is hi, tau I, and nu I. Hi is the channel gain or path gain corresponding to that path. Tau I is the delay because it is traveling certain distance, and then this also goes through some Doppler shift. So this is called OTFS channel model. And then from H, which is we call impulse response, the delay time response can be obtained. I'll try to explain that by sampling. In fact, let's say that by sampling t and tau and t at delay resolutions, the tap delay line channel model is obtained. That probably will skip this. Point is, you are describing the channel in terms of p number of paths, p number of taps, and each and then you need to account for different values of tau and different values of nu, or different types of time delays and different values corresponding to Doppler shifts. So which means that you need to come up with some sort of a you need to discretize delay, time delay, and Doppler shift appropriately. Okay, hope you see the point. Hope you see. So basically, to implement this, you need to think about how do I divide time delay into slots and Doppler shift into slots, and that's exactly this grid corresponds to. So what are you doing here? There is a delay is divided into m number of grid elements, and Doppler shift is also divided into n number of discrete intervals. Right? So this is a interesting design that we need to do, and to do that there are some constraints between delta f, that means the resolution of delay, and the resolution of Doppler shift. There are some relationship between the two, and let's see. I think you will see them, but otherwise I will leave it for you to for the ground. There are these constraints have to be maintained. For example, if you increase this, this gap here, this will be the gap. The resolution of the delay domain will be appropriately changed. So more importantly, I think if you look at this time frequency grid, here is a t and here is delta f. If one increases, the other will reduce. This is standard in time frequency domain, meaning that if you increase the time interval, then the interval in frequency domain will be reduced, just like a Fourier transform, duality of Fourier transform properties. Here also, there is a relationship that here it is. The relationship is t equal to 1 over delta f. That puts the constraint. That means if you increase t, delta f will be reduced, say, and vice versa. That has to be maintained. So we talked about demodulation, and let's look at the context of where we are going to apply. So far we learned that how to design a OTFS system, and what are the processes involved, and what are the mathematics involved. But now we look at the context. The context is we would like to use OTFS for satellite communication. And how does satellite communication work? This is you can also get this picture from outside. In fact, there are some papers, 5G non-terrestrial networks 2024. I think probably you should review this. And some of these pictures are coming, whenever you see a reference, the information actually, the source of that information is this. So there are three segments. One is ground segment, and then control segment, and the space segment. So say as opposed to cell tower, there is a user and a cell tower. There's only two things, two components. But here there are three components. In the space segment, there are satellites, and of course there should be some links between the satellites, and then in here is the user. User has a phone, and there is a link between this is a satellite to ground link, but there is another segment where it's called control link. You won't do everything from the phone. Your phone cannot control the satellite. So there is a control segment somewhere on the ground that takes care of what you call tracking and control. So this is different. This is transparent to user. So if you look at any satellite communication, you will see these three segments. So satellite communication consists of three segments: ground, space, and control segment. The ground segment maintains communication between terrestrial networks. The ground segment, these two, actually sorry, ground segment handles the communication between the on the ground. Space segment consists of satellites. Think of like LEO satellite for now. Actually, the topic is about LEO satellite communication. And the third is control segment that tracks the position of satellites and handles the telemetry. So this you probably won't see. Okay. So we are focusing on only these two. We're not worried about. We're not discussing control links or control segment. OFDM modulation scheme could be implemented in the space segment. The Doppler precompensation unit is implemented in the ground segment. So obviously, when you focus on the downlink, there are two things: downlink and uplink. When you say downlink, what exactly you mean? Satellite, your transmitter is in the space, and the receiver is on the ground. Of course, communication is two-way; it's not just one way. And there are similarities. If you understand, typically when you read a paper, they'll say, "Oh, we are focusing on ground link." Downlink. What does it mean? They're focusing on the transmitter in the airspace, in the space, and receiver on the ground. It could be the other way too. But some, like in this paper also, we're focusing only on the downlink. Similar concepts can be applied on the uplink also, but right now focus is only on one link. So what he's saying is the modulation technique. If you employ OTFS modulation, of course you need to have transmitter here and receiver here. So transmission part is implemented here and receiver part is implemented here. And here are some of the results. The focus has been only on the BER for now, bit error rate. It's only one metric, and so look at the parameters. We considered OTFS and OFDM at 500 kilometers speed. So this is a typical speed of an unmanned aircraft system. So remember, yeah, this basically, in real right now this is not satellite speeds, but when you implement or when you put this scheme in the context of satellites, these speeds are not enough. So for now, let's say ignore the satellite communication and focus only on the drone to ground. Okay, so in that case, 500 kilometers per hour are reasonable. I'll come back to this, but if you are if you think about satellite speeds, yeah, this diagram, this plot is about satellite communication. The one before is only for drone to ground, but this is the satellite communication link. So LEO satellite communication speed is 27,000 kilometers per hour. That's very high speed. So I'll come back to this. What I was trying to say is that this technique, this graph is applicable for not for satellite, only for drone speeds. So this graph shows. Let's understand how this graph. Here is the SNR, and this is the BER. This curve is standard. If you see any performance plot, you're going to see SNR versus this is the channel SNR, and this is the BER. And what is that we are saying? there are three graphs, OFDM, single tap. So what do you mean by single tap? Let me explain that for a minute. Here, each one is a tap. So how many taps are there? P taps. It's like a filter. In a filter, you count number of taps. But what actually these taps are corresponding to? They correspond to number of paths. Okay. So P number of paths are there, but or P taps are there. But in this example, we are only considering one tap. So that means practically you are ignoring all the non-line of sight. So only direct line of sight you are considering. Okay, so that's where you can interpret. So one tap is considered, and what is delta F is the spacing between carriers. So spacing between carriers 30 kilohertz. So that means it's like, if you think about frequency axis, you have first one is 0, second is 30 kilohertz, then is 2 times 30 and 3 times 30. You can think of like that. And remember the T equal to 1 over F. You have to maintain that relationship too. What are N and M? N is the number of symbols, and M is the number of subcarriers. Right? You are able to think about the grid. So that is the context. And the red one is delta F equal to 60 kilohertz. That means intercarrier spacing or subcarrier spacing, it's called subcarrier spacing, is 60 kilohertz. So what does it mean? Look at this. Now M is only 32. What happened? If your spacing is 30 kilohertz, you are able to have 64 subcarriers, but now increase the subcarrier spacing to you doubled it. So it means that number of subcarriers are reduced to 32. You can see, you need to maintain that relationship. So if you increase the spacing, you will have only less number of subcarriers. On each carrier, you only transmitting one symbol. See, N is the symbols. So remember, what happens when you increase the subcarrier spacing? T will be reduced. That means symbol time will be reduced. Okay, so that's the relationship. If you increase delta F, that means symbol time will be reduced. So you can put more symbols. Okay, but subcarriers, okay, I understand your question. You're saying, okay, you're right. How are you sending, you're using 32 carriers, and how are you increasing the symbols, right? Yeah. So you're sending more symbols then. Yeah, you're right. Yeah, that's also there. Now you don't use all the subcarriers. You don't use all subcarriers for information only. Okay. So the key thing here is, so just for comparison, you are showing two different OFDM graphs, but the yellow one corresponds to OTFS. MRC stands for maximum ratio combining. So that's the decoding technique. But ignore that. So quickly, the lesson, the conclusion or the observation here is that for OTFS, you can see the BER is better, much better. That's what we wanted to show to begin with. The second is, of course, OTFS has been studied by other people. So what is new here? All we are trying to do is, we want to see the feasibility of applying OTFS for satellite communication. That is demonstrated. But it's not that you're suddenly applying the same idea to different technique. You need to play with these resolutions, how to choose delta F, how to choose number of symbols. All that also has to be chosen. It's not just directly porting one, just changing the parameters. It's not just changing the parameters. So if your speeds are 27,000 kilometers per hour, then appropriately you need to choose the resolution. So I will skip what goes on behind the screens to how do you choose the resolutions for now. But the point is, it's not just you're not just changing the numbers randomly, but they need to take into account the resolution of delta f and t depend, or symbol time and subcarrier spacing depend on the maximal Doppler shift you are expecting. Okay. So you design the time frequency grid or delayed Doppler grid. The delayed Doppler grid is designed in such a way you need to take into account what Doppler shift, how much Doppler shift you are expecting. Obviously, it is clear, right? If how much the maximum Doppler shift you are expecting has to fit in this grid. Same way, once you choose the maximal Doppler shift, then accordingly you have to adjust the delay, because there is a relationship. So that's also some sort of what you call alignment. So you cannot just randomly pick them. Okay. So that is the work. So the question is, for example, when we send this paper to ICC 2025 to the main conference, the questions were, either the reviews. One of the reviews said, they just applied the known technique to a different context. So what's the big deal? What is new? So it depends on, of course, how you write the paper. So in the next round, when we submitted the same paper for a workshop, then we use the feedback to explain what has been done. It's not just applying the same technique or same idea, one idea into some other context, but choosing the grid, choosing the parameters appropriately to deal with the large Doppler shift that you are encountering in satellite communication. So that is the novelty. Okay. Okay. So this is the preliminary result. What is the point? We are looking at lower speeds, only 500 kilometers per hour, which is not applicable for satellites. But then what happens if you do? Okay, let's look at this first, and then we'll come back to the other two slides. So this here we're saying OFDM versus OTFS for satellite speeds. What kind of satellite speeds? Even though it's not mentioned here, we talk about 27,000 kilometers per hour. So there also shows that OFDM compared to OFDM, OTFS has lower bit error rate. So it's quantitatively we are showing that it is good. Again, again the question is, it's not enough to show, oh, I'm doing better. When the people will say, oh, it's already been done, it's already been shown, already been done. So what is new? You have to say, what did you do to get these results? So that is the crux. It's not sufficient to show one plot and say, I'm done. You have to explain what are the insights you gained. How did you choose the resolution of delta f and t? And that will allow the reviewers to see the contributions, okay, or novelty. Now, my student also has done something else. He said he looked into capacity of OTFS scheme. So even for OTFS, there is a zero padding to accommodate for to handle the inter-symbol interference and inter-carrier interference. You have to do some zero padding. Remember, we talked about padding. Why padding? Padding is to give room for the shift. So, for example, let Z be the length of the zero padding. You are wasting the space. You are wasting. But all you are sending is sending zeros, putting zeros over there. So if M is the actual number of subcarriers, N is the number of symbols, then here we are using M dash times N. And what is that M dash? M dash is M dash is actual number of data symbols. Even though you start with M times N, but out of M symbols, M minus Z are actual data symbols. Okay. What about Z? 0 is just padding. I hope you are able to connect, right? So that means you are wasting. Why are you wasting? Because you want to handle you want to address the inter-carrier interference. You are giving room for the inter-carrier, handle the interference. So which means that out of M symbols, Z symbols are wasted. You're not passing any information. So actual data is only M minus Z or M dash. So he did some simple calculations. It's nothing involved. So he's saying if you say HQ is the entropy and P is the probability of error, then you can define R or rate. In other words, maximum data rate is capacity. So we're trying to see what is the achievable rate in OTFS scheme, and he did some small simple calculations here, and you can see the number of possible data bits are 2 power 2 times m dash times n, and that could be expressed as and out of that, both are same actually, 2 power 2 m dash n times HQP bits can be so this you can look at these definitions of entropy, and point is this is coming from basic book from. So he computed the maximum data rate that you can achieve, and of course that is our capacity, and he did some calculations on that. He plotted capacity when the delay spread is 710 nanoseconds. What is delay spread? Delta based on the delay spread, you are choosing the t. Your symbol duration has to be increased if the delay spread is going to be larger. So you can consider it basically like this is nothing but t. So your symbol time depends on the delay spread. If there is more delay spread, then you have to increase the symbol time. So take a look at this. So basically we are plotting the capacity with different delay spreads, and this should be also logical or common logic to show that the capacity will increase if the delay spread is small, right? What means if symbol time is small, if delay spread is small, then symbol time also could be small. If symbol time is small, symbol duration is small, we can send more symbols. That's a simple logic. Okay, so basically you're showing that even though it is kind of known, but we are just plotting that for smaller delay spread, it is you can expect more data rate, and for larger delay spread, your actual information is number of symbols that you can expect, or capacity is going to be small. This is nothing new, but he just added one more metric. BER is one metric, and we are also showing the capacity. Remember this, in some sense, BER is connected to capacity. What is the definition of capacity? How many bits you can transmit per second or per hertz with minimal error rate. So which means that if BER is bad, then capacity data rates also, achievable data also will be small. Okay, in conclusion, this research demonstrated that OTFS is useful for high mobility, and we are able to show for two cases. One is 500 kilometers per hour, and also 27,000 kilometers per hour relative speeds. There's a lot of work going on in OTFS. It is not only useful for addressing or dealing with Doppler shift, but also useful for joint sensing and communications. And for all this work is, what we discussed is some fundamentals. We didn't go too deep into the techniques, or we didn't discuss the other applications of OTFS. But this is the beginning. So this is ongoing work, and OTFS is a good technique to specifically deal with Doppler shift. And now I want to show you some insights into what do you mean by symplectic Fourier transform. Okay, and the other thing is how can you say OTFS is immune to Doppler shift? So I did some work today morning to give you some pointers. So the question is, how is OTFS is immune or resilient? You can also say resilient to Doppler shift. Okay, so it is highly resistant to Doppler shift because it looks at data in delayed Doppler domain instead of time frequency, and this representation naturally aligns with the characteristics of wireless channels, especially time varying environment. Again, I will leave it there. This is a high level description, but you need to do more investigation on your own. Second is, OTFS spreads information across both time and frequency dimensions, leveraging full diversity of the channel. This prevents localized frequency distortions. Frequency distortion means, example is Doppler shift, from significantly degrading performance. In fact, my student says this OTFS technique is converting, the way he describes, converting time varying channel into time invariant channel. That's how he says. Okay. So earlier I was telling about that OTFS actually employed Zach transform and some Wigner transforms, but in our presentation we didn't see any of those. So over the years the technique has been simplified, and that's what you are seeing in the today's presentation, because I didn't discuss all this. The other thing is, something else is, what exactly you mean by what you call delayed Doppler domain, and what do you mean by symplectic transform? So there is a little bit of discussion here. Yeah. OTFS leverages the concept of phase space representation. Phase space representation is commonly seen in physics. So it says, what do you mean by phase space? There are two domains. It describes this data in pairs of conjugate variables, such as delay Doppler. So even time frequency also dual representation. So for example, normally when you generate a signal like audio signal, it's a time domain. It's only time domain. But when you represent, take the time domain and convert it into Fourier transform, you are looking at a frequency domain. But there are techniques where it's useful to look at both time and frequency at the same time. It's called joint time frequency domain. So the phase space representation is something like that. Same thing with delayed Doppler too. So basically you are looking at the data in 2 dimensions. So increase the, basically like a joint representation. Okay. So time frequency domain or phase space or delayed Doppler, these are called joint representation. So unlike traditional time frequency analysis, phase space representation retains both variables. So somehow you are increasing the, you're blowing up, 1 dimension to 2 dimensions. So there is rich data that rich information that you can see, and then you can make use of it. So let's review this. Key benefits of phase space representation: 2-dimensional mapping. Signals are placed in delayed Doppler plane, allowing a more structured interaction and more understanding, more insight into the data as well as the channel. Improved signal resilience, and so symplectic Fourier transform is basically transforming a signal from time domain, from delayed Doppler domain to time frequency domain. So these are all It's called joint representations, joint time frequency or delay Doppler or phase space. These will allow us to get more insights into the data. So here are some comparison between OFDM and OTFS. OFDM is time frequency domain, and OTFS is delay Doppler, and impact of Doppler in OFDM is it causes intercarrier interference, whereas in OTFS it is easier to handle because it converts the Doppler shift into phase shift. And point is, they say it's easier to handle. And full diversity is utilized in OTFS, and mobility handling is better in high speed cases with OTFS. So this is a summary. Yeah, once again, you might have learned to some extent, and by doing a little more study, you should be able to get more details about OTFS scheme and why it is suitable for satellite and drone to drone communication. All right, I'll stop here. And if you have any questions, you can ask now, but otherwise we can meet in the afternoon actually. Okay, I'm going to this presentation I recently gave um, to an audience of National Security Innovation Council. So I was asked to represent my university and I gave this talk. So that was, you can see that's March 3rd, just before coming here. Okay? So what started as a research and development about 6 years ago, about in 2018 it started, but actively this work started in 2020. The topic is advanced air mobility, and it was called, to begin with, it was called urban air mobility. And I happen to be actively engaged in this project, and I call this next year of aviation, because if everything goes well as planned, sometime soon, like before 2030, you are going to see air taxis in the real world. And it is not too far-fetched, because in 2014 we started, I was also part of the project. The NASA in the US, NASA led this initiative called UTM. UTM is basically, even though it says UTM, the expansion is unmanned aerial or unmanned aircraft systems traffic management. It says it's about traffic management, but however, it's all about drone deliveries. So if you search on the internet and then look for UTM, the project is about bringing drone deliveries to the real world. So it started in 2014. By 2024, it became a reality. It takes time, depending on the country and depending on the regulation, how strict are those regulations. It takes time for evolving. But today, as we speak, yeah. As we speak, in the place where I live, in Dallas, Fort Worth, there are drone deliveries that are happening. So anything, small burger, you can order. You can order some medical supplies. More real world, more important applications are like some medical supplies. You can try. You can ask for delivery. They don't. The drones don't fly too far. They are only about for 2 miles or 3 miles. Then the weight cannot be too much. Probably up to 4 or 5 pounds. That means about a couple of kilos, 2 and 2.5 kilos. But still, these deliveries are happening. Nobody is making money, but it's in the beginning stages. Same way, air taxis concept were conceived in 2020. So this is called advanced air mobility, and the small drone deliveries, the project is called UTM. So what does it take? And in my university, we have a center called Center for Integrated Intelligent Mobility Systems, called SIMS, and there are many faculty who are working together, and this is a kind of supported by this center. There are several centers right in Warangal also, right? So every center is proud of contributing to research in some direction. So our center, this center is contributing to this topic. All right. So, and I'm proud of this work because I'm personally involved. I spent a lot of time, and I'll show you what I have accomplished. So notice that we're not talking about mathematics here. We're only giving the direction of what kind of research application, more like an application. Okay. So here are the things. You're going to see brief discussion about the university, the center, and I created a group. I'm the, what do you call, at least co-lead. The two of us together created something called North Texas Cohort. It's like a group of entities consisting of government, public sector, private companies, small and big companies. So we created that, and together we were working on this project called Advanced Air Mobility. Then I'll show you what exactly it means, what are the things that are going on. and also talk about what we've done so far, ongoing projects, and what we are going to do in future. So this is a very ambitious project, but I'll describe it to some extent in a simple way. So our university started way back in 1890, but then my department was started in 2004, I believe. Yeah, so it's about 20 years old. So not too old a department. It's a new department. And then this is the center I was talking about, Center for Intelligent and Integrated Mobility Systems. So to some extent, I'm responsible. I'm also what I call responsible to have this kind of this center. And as part of it, we created a big mesh. It's called outdoor mesh. And the idea here is the dimensions are large, it's like a soccer field kind of size. Think about 130 feet and 180 feet in one dimension and 300 feet in the other dimension. So 300, 180 and 130. So the height is 130 feet in feet. Okay. So what's the advantage of this? You don't have to take permissions from anyone. You can fly as long as you are flying the drones within this. Suppose you build a new drone, you can test. And suppose you want to test drone to drone communications, you can test. That's a benefit. So it will be supported through, right now to build this, it costs about $1 million, but it's not complete. We still need to put cameras, Wi-Fi networking, and even probably some sort of a small base station. All these things we want to do in future. And these are the two people who are, one from College of Engineering, one from College of Business. So we're working together across the colleges. This is important. Collaboration can only happen, or interesting results can come only when we cut across the disciplines. So otherwise, some interesting applications are not possible. For example, I had 2 grants together with the College of Business. So one thing that I'm doing is, let's say we talked about disaster response. So we need to have flying base stations or flying cell towers. But then you also have to see what is the role of this technology that you are building in terms of how they are synergistic with what goes on among people, and how it helps people to coordinate activities, and how it helps to connect organizations too. So for example, in disaster relief operations, the idea that I try to pursue is that when something happens, information has to percolate from the place of, or the scene of the accident or a disaster all the way to the decision makers, so that the resources can be supplied or obtained in time. For example, if you see somebody having a heart attack, then in an emergency scenario, then we need to see what kind of devices we need, what kind of medical help is needed, and then that information has to percolate all the way to the decision maker so that you can get the supplies. So to do that, technology alone is not sufficient. You have to have an idea about how technology can assist in speeding up the process. So how technology can help humans, or how humans can utilize the technology and the gadgets to make sure that you get what you need in time. So with that, we do a lot of surveys. For example, when I work with College of Business or social scientists, they do some surveys and say, okay, what kind of technologies you are using now, and how they work, and are they meeting the requirements, and if you need more support, what kind of things you need. We do that both offline and during the emergencies and normal times. At the end of the day, the key thing is the collaboration between engineering and social science or businesses will help to do things better. Okay, here is what I call a cohort that I built. Today I was just walking down coming from the in the showcase, research showcase, or research industry and academic collaboration showcase or exhibition that's happening somewhere near. So that is something that I pursued interestingly on my own. I started on my own, but then all these companies joined. Like if you have I don't think I have a lot of leadership skills, but at the same time, when I said I'm working on this, then a lot of people joined. And look at this. This is my university, and there's another university, Texas A&M. They have something called Autonomy Research Institute. And then Bell. Bell is it used to be a helicopter company, but now they don't call Bell Helicopter, just say Bell. And it was also became a part of another company called Textron. The point is, it's very well known. Bell helicopters are very well known. So they also participating, and these are all small companies. And this is something called demand capacity balancing service. So we'll talk about that in a minute. And this is a small company. I'm called Hermes Autonomous Air Mobility Systems. I'm partly responsible for creating this. I'm kind of a advisor to this company. And this is a small company. This guy, their CEO lives nearby in my house. He's in Frisco. And this guy built a traffic management system at home. And then of course he has a few people in India. There's another local India branch. But he developed a terrific traffic management system, and I personally saw it's performing as needed, as expected. And this is a weather solution. It's also a startup company. But what they do is they analyze local weather. Of course, they deploy sensors. In fact, if I am right, they send a balloon, I think, every day in the morning to estimate the weather at certain heights. Because whatever weather measurements you collect on the ground, they are not sufficient. They don't capture the weather at high altitudes. Like for example, if you are flying drones at 400 feet or 4,000 feet, then you need to be able to model weather at that height. So ground stations will provide you to some extent the information the data you need, but that's not enough. And this is, by the way, these are all startup companies. So this is what I call council of governments. So what does it mean? There are about 30 municipalities or suburbs in North Texas or North Central Texas. Like for example, if you heard the names, let's say Hyderabad and Secunderabad. They are two different cities, right? Maybe Nacharam could be another suburb, or BHL, that's another suburb. So think of like local governments, and there are 30 such governments that came together, and the council was formed as a conglomeration or collection of these governments. So what it means is that the needs of the community and needs of the suburbs are discussed. What do they need? What kind of services they need? And what kind of technology needs they have? All these things are discussed in this council. This is also a private group, but they also are actively engaged in improving the facilities or technology solutions in Texas. The point is, somehow it worked together. So I had I didn't really have a big plan or everything, but the moment I started this initiative, I engaged with NASA and Advanced Air Mobility. All these people started, they came together to work with me. So I'm serving as a lead, academic lead, but there is also a industry lead. Of course, that's the partnership. It naturally evolved. I didn't really put a lot of efforts. And what we were able to do, I will tell you more. So here, I'm saying why a university has to involve. Why does industry require academic leadership? Because we think far ahead, far into future. We come up with ideas that the society needs 10 years down the lane. That is the power of academics. Whatever the industry needs some solutions today, but what does the society need in 10 years? It's what we do, what we think. So that is what I tell. So I'm providing the academic leadership to this whole group, that we just saw. Then some of the action items are, you already know that I spend a lot of time on vehicle-to-vehicle communications. And to begin with, around 2014 or 2015, I started this ad hoc networks or airborne networks. And then it happened, so it's very timely. Sometimes you don't know where you get inspiration from. But by 2017, I published a book, first book in the world on UAV communications and networks and communications. That was published by Cambridge University Press. That was my first contribution. And then, as we speak, I'm working on another book. I think the book is called Unmanned Air Transportation: Bridging Principles to Practice, or Bringing Principles to Practice. It is, so point is, yes, somehow, so you get inspiration from some place, some source, but then by working hard and then focus, having keeping the focus on whatever goals you have, it is possible to achieve a lot of things. And probably, I think I'm in the next 10 years is my peak. I'm in the peak of my career. In the next 10 years, I will be, I want to do as much as I can. So with that, I'm actually taking this work very seriously. So these are my goals rather. And interestingly, my university also is supporting a lot. Whatever I want, they give me. So with that, I'm able to. I set myself big goals, and then everything is helping. The environment is helping. The university is helping. So with that, I would like to continue my efforts. So now, what's interesting is that that as a group, as a community, it's not that university alone. We are working with all the universities in the group, in the region, on a community, like with like as I said, I talked about Council of Governments, right? So it means the Council of Governments I was referring to, that it takes care of 30 municipalities. So it's overseeing or guiding or supervising 30 municipalities. So that group, as well as all these companies together, sorry, we are coming up with, we have some plans. So what are kind of plans? One is something called building airspace laboratory. So what is it? What do you mean by? Initially I thought, oh, laboratory is like a lab, something that we have in the school. I have a lab. It's called Autonomous Systems Lab, but it is still within the building. But the Council of Government, or the person who actually responsible for or leading that Council of Governments, he said airspace laboratory should be outside. You're talking about airspace. So and then I'll show you what is our idea of airspace laboratory in a minute. Maybe let's skip for a few minutes and then come back. This is what we are talking about, what we are calling as airspace laboratory. So this is about 3,000 square miles area. This is in the city, in the geographically. For example, let me show you some part. This is where my university is. We call our university engineering campus as Discovery Park. For a good reason they put the nice name. And then this is airport, the major airport in the city. And this is we're calling that heliport. It means in future, it's not now. I mean, you can fly a air taxi from the airport to this location, and I live very close by. And this is my university, and this is we're calling what is vertiport, by the way. It's like airport. It's only for drones or like helicopter size vehicles, not a American Airlines or Delta. No, all those big aircraft go from here, but they are also trying to build a terminal just for drones. So look at the spirit. It's not like some work is going on in the university, but it is happening in the community, within the community. And so we are going to designate this as it's only a plan. Nothing happened so far. Obviously, when I did some estimate, it cost like anywhere between 50 millions to 100 millions. It's too expensive, but we have a grand vision. This is what we are thinking of. So what's interesting is, of course, you can fly a couple of drones and say, oh, take photos and enjoy, but that's not what we are trying to do. We're trying to get ready for this kind of air taxis. And this is happening, this is only one side or one region. I'm sure several other cities are preparing for that too. In fact, as many of you know, I'm associated with Tihan Institute in IIT Hyderabad. So when I visited their place, I saw nearly 100 to 150 drones over there. And then there is a big campus, of course, and then there are a lot of self-driving vehicles. I saw a wind tunnel. So the point is, potentially, with proper support and funding, probably, the similar things can happen in Hyderabad too. So every country and many parts within the country, many regions within each country are also preparing. So this is our preparation. So we are saying that let's create a airspace lab and create a network of airports. So the point is, yeah, something comes to a DFW airport, and from here you go on different routes. And what for? One is for transportation, but more importantly, you can build more what you call real world applications, like time critical applications, such as some of you may be knowing some like human tissue and organ transportation. So just to give an idea why we need drones, it seems that every hour organ is outside the human body, it loses 10 years of its life. That means if there is one hospital where the donor is, and then another hospital where the recipient of an organ like a kidney or some other human tissues, you need to deliver it as soon as possible. As soon as you take it out, you should deliver it to the recipient. So sometimes, yeah, basically it's a very time critical thing, time sensitive transportation. So you can do those things. We're not talking about pizza deliveries and those small things. So with this kind of preparation, if this becomes successful, a lot of wonderful things can happen. So anyway, this is what I meant by a airspace laboratory, outdoor facility, a large facility where you can test the experiment with conduct a lot of experiments on real world flight tests. Okay. And yeah, I'll come back to this. So this is what we are trying to prepare for. Okay. So I talked about our vision is what we're trying to prepare for building a airspace laboratory. Second is creating routes. Where do we fly? Right? For example, I showed you the network practicality. So how do the routes are determined based on the commercial requirements? For example, this route I know very well, but here there is very what you call highly. So the city of Frisco is technologically very advanced. So there is also something called PGA, Professional Golf Association, I believe. So if that is located here, and then in 2026 there is going to be a big World Cup for it's called FIFA. Some of you may know. So all these are happening, right? So it's for people who are coming from faraway places and they want to cut down the commute time. From DFW to airport to Frisco, they can fly in about 5, 10, 15 minutes. Again, those are for commercial applications, but more time critical applications are things like patient transportation. Okay. So obviously, somebody has a heart attack or something, somebody is in an accident. Even 1 minute counts, even 5 minutes count. So for those applications, you can use these routes. So for example, about each segment is about 30 miles. So to fly 30 miles probably takes about 10 minutes at most, including takeoff and landing. So those are the applications we are talking about. So when I said identifying the routes, that's what I meant. Which routes are commercially feasible. And then where do we construct this vertiports or small takeoff and landing facilities? And then what kind of services you need? This is something interesting, something important. How do you provide communication? We talked about airborne networks and communication. So the key thing is, how do you provide, what kind of infrastructure you need to provide communication support for the corridors? So as I said, usually you need, on the ground, you need to build this infrastructure. You need to build the base stations specifically for providing communication support for drones. You need to have some, you need to have the base stations on the ground. And then you also need a radar. We talked about weather service before. Radar is to detect non-cooperative vehicles, meaning that you need to know, obviously for safety point of view, we need to know what is in the airspace. That includes drones that are flying without permission. Also, I'm calling that as non-cooperative vehicles. Or suppose you see a big flock of birds, then we need to know too. So radar is definitely required. It costs about, depending on how much area we are trying to cover. Suppose you want to cover 10-kilometer radius. I think it may cost about $1 million. So we need a radar. So every airport, wherever you are having a vertiport, you need to have a radar. And then we also have plans to connect with a tribal. There is a tribal region close by. It's about 100 miles. So if everything works out, we want to actually have a route from urban to rural areas. Why is it important? In urban areas where technologically advanced cities, and you have a lot of facilities, taking a patient from accident scene to the hospital is very quick. Probably 15 minutes you can take them to the hospital. But if it is rural, as of now, I mean, average, it takes anywhere close to an hour. So 1 hour is too much. For example, if somebody has a brain stroke or even heart attack, the sooner you go, the better it is. We have seen many cases where if you lack of facilities or services like ambulance will cause fatalities. Okay, so with that, so we want to connect with rural area. In fact, urban to rural area. That's the key idea, and there are tribal regions too. The main point is we still need to think about what kind of applications or what kind of things we can transport. For example, probably it's not economically feasible to transport fresh leaves or fresh green leaves or fresh vegetables, but still it's a good application. It's economically probably that's not so lucrative, but definitely fresh vegetables can be transported using drones from rural to urban, from agricultural areas to urban area. And then of course you need a lot of funding. For now you don't have, here it's not important. So this is our collection of our group of partners, universities. By the way, if you want to know which universities are in Dallas, there are UNT, Texas A&M, Corpus Christi is a little far, about 300 miles. UTA, University of Texas at Arlington, is again in Dallas. There are 4 major universities: University of North Texas, University of Texas at Arlington, University of Texas at Dallas, Southern Methodist University. So 4 universities are located within the 30-mile, 40-mile region of Dallas. And there is also Texas Women University. It's not that well known. Texas Christian University, those are smaller universities. But these 4 are major universities. They're all public universities. Then other things, we talked about municipalities, North Central Texas Council of Governments, a big company, parent company of Bell, tribal government, and this Joby Aviation is a new company, very successful in developing or building air taxis. So in fact, air taxis are already there, but they're not flying because first of all they need to be certified, and we need to have regulations for safety and security point of view. So the plan is in 2023 there was a document that came from FAA, Federal Aviation Administration, that by 28 they want to see air taxis becoming a reality. So the plan is to have pilots on board to begin with, even though you are flying autonomous flights. So the plan is to have a pilot on board for a few years, then slowly make the flight autonomous. So notice that the emphasis is on autonomy. So the flight has to be flying, it has to fly autonomously. So many companies, we are all working together, and that's how we are preparing for future. These are the flight demos. So we want to have routes, this kind of routes we're talking about, from here to here, see, like a hub and spoke model, right? So there are two main things. One is DFW airport, and also there is another airport called Mineral Wells, a small regional airport. We want to use this for a demonstrations, but these are real routes. So this for testing, this area is for testing and experimenting, but this area is for real flights. So this is some data there. Somebody asked us how many operations are going on, how many flights basically were flying. So there's some numbers here. So what this says is, in DFW airport in year 23, 731,518 flights either landed or took off. Okay, now this is the work that I was personally engaged in. On October 11th, we have demonstrated very first air corridor in North Texas, extending from airport, this one airport, to this is a commercial airport, to UNT, my university. So this was done on this day, and it was featured in a NASA website. I published an article in IEEE Spectrum, and I gave a TED talk. So this is my personal accomplishment, milestone in my career. So this is what I was able to accomplish. So I led this initiative. So what exactly we did? Look at this. This is my university, my campus. So from my campus, we designed a route to fly about 30 miles to an airport and then back. Obviously, we don't have a vertiport, so we could not land here. But instead, here is an airport. So Bell helicopter took off from here in the red route, and then it returned back to this. And we flew 2 rounds. And what the idea here is, we pretended as if this helicopter is an autonomous flight, and we tested a lot of autonomous features, like for example, getting telemetry from the aircraft, sending command and controls autonomously. Then we also changed the flight route in the middle. So all those autonomous features we were able to demonstrate. So this is the very significant milestone personally as well as for Texas. And then, so what does it take when you talk about corridors? What does it take? So here are the one vision. We want to have 4. It's only a planning. It's not that we only planning. We're trying to do that in future. So 4 locations we want to have vertiports. That means, what is a vertiport? It's like a takeoff and landing location. It's like a rooftop, maybe 2-story building. People will be sitting on the ground, 1 floor, and on top rooftop, the drones will land, taxis will land and take off. And then you can do a lot of research within the building. And then we want to have communication support. So at every vertiport, we want to have a base station. Then at every vertiport, we want to have a radar. C2 stands for command and control link. And then there's something for research point of view. We want to have a laboratory called pilot behavioral research. The question is, how many flights one pilot can monitor, and how much stress a person will have when you are working on with the drones, and how many hours a person can work continuously. So those kind of studies we want to. So this is where, again, interdisciplinary research. So that's our vision. And remember, CNO is all these are local within the dialer. So last one is a tribal region. Choctaw Nation is, it's like a tribal region. So this location is somewhere far. So these are all other three are located locally, but this is some about 120 miles away. So in phase 1 we want to have one corridor. Phase 2 we want to have another corridor. By the way, Denton is where my university is. Frisco is where I live. So it's like if this becomes a reality, I can go to work on drones. This is not a fiction. This is the idea, that this is the plan we have. Okay. And this is the phase 3 is a long thing. Now of course it costs, right? How do we make this happen? We need to get funding. And how much funding we are looking for? About but whatever money we get, we build, we use that and build slowly. And to really accomplish this goal, this costs like probably about $100 million. All right. Now let's take into what is that for us, what is for you and me. The first thing is, these are the challenges. Autonomy. Autonomy is a complex topic. You are saying the drone or the air taxi has to fly on its own with almost like no intervention from the human being. But at some point, we have to involve. Suppose, you can't sit in a self-driving car. I don't think, no matter how advanced it is, you can't sit idle. There will be a point where you have to take over. Okay? But there are some interesting questions just for you to think about. Who should have control? Is it vehicle or autopilot or you? Number one. Number two is, in what situation the control, you have to take control, or in what situation the vehicle has to take control. Suppose, say you have some heart problem, maybe you're feeling dizzy, then it will be good the car actually take control and takes you to a safer place, right? So think about, there are many scenarios in case of drones. I personally think when I spend some time thinking. So one is, let's say couple of us, you and me, and flying in a drone, and only two of us, no pilot. Then if a bird strikes, then what do we do? A bird strikes the plane and there is some damage. You have to handle, right? So how does autonomous system handle that? There are solutions, but I want you to think about. Second is, suppose, say I don't feel comfortable, I'm feeling very uncomfortable, and I want to go home. And suppose an old lady is sitting in this. I don't know whether it will be old senior people willing to sit in an autonomous flight. But if, let's say, anybody, an older person sitting, was brave enough to get onto the plane, but he or she may be uncomfortable after some time. Then what do you do? Who do you talk to? So those are the questions we need to answer. Autonomy is not an easy thing, especially in the air. On the ground, at least you're on the ground. But in the middle of the air, something happens. When I was younger, like 30 years ago, I did skydiving once. It was scary, but it was fun. So so point is, you may be brave when you're beginning, but after, particularly from the plane, of course there is some person who will skydive with us, especially in the beginning. That means you tie down, and there is an instructor and the tourist. Like I'm the tourist, so I said, okay, with some of my friends we went there, and then the instructor actually will take care of everything. But still, you may not. After going there, some people may not be ready to jump. So same way, people may be brave enough to sit in a drone, but then when it comes to when you are flying, maybe you can become uncomfortable. Then what do you do? So those are the questions we have to answer. In addition to, there are many questions. These are a couple of points I maintain. So autonomy is a big topic, and I'm going to cover this tomorrow morning. There's something called human autonomy teaming. I'll give you a good review of, I call 50 years of research in human autonomy teaming. I'm going to discuss that tomorrow in very simple terms, no complicated models or mathematics, no geometry, stochastic geometry or point process, just a simple discussion about human autonomy teaming. We'll talk about that tomorrow. But then traffic management at scale. And by the way, this has to be done through software. Like I was talking about earlier, one of my person that I know, he developed the traffic management in his garage. So it's possible to do that. Communication support, we spent almost like 10 lectures on communication support. Air-to-air conflict management, what does it mean? Yeah, multiple drones are there and a couple of drones have to negotiate. They came so close, but they have to avoid conflict. So there are, I think I mentioned a couple of times, they're called tactical, strategic conflict management, tactical conflict management, operational conflict management. Basically, you're trying to address conflicts in the airspace. That's what I call it. Security and privacy. Community acceptance. How do you convince people that, oh, we are flying drones in your area? So one drone, people clap and then, but if you have 10 drones flying every day, every hour, then maybe nuisance. So how do you convince community that okay, drones are good for you? Now there are a lot of benefits, even though it's noisy, but still it is good for the community. How do you know? And then other thing is regulations, practices, and ultimately, how do you prepare for the future workforce? Okay. So these are the research challenges. One second. Wait. Just take a minute. It's frozen. The screen is frozen. Give me a minute. So we talked about these corridors before. I've always been using this line as a corridor, but so this is the problem. One problem is autonomy in airspace. So how do you build this autonomy in airspace? One is you need an autonomous vehicle. The other is somehow you have to figure out how they are going to fly, and at the same time, from the ground you should have reasonably able to control the flight. So one idea is we build this concept of air cells. So you saw that the first paper from my lab, it was published in 2021 on air corridor, the concept of air corridors we published. And this illustrates two things. In fact, we talked about vehicle-to-vehicle communications, and that is for cooperative vehicles to communicate with one another and avoid potential conflicts. At the same time, if the one vehicle is, like for example, here is a obstacle. So we call that as a airspace hazard, like a cloud, a thick cloud. Now remember whenever you fly, when the flight actually goes through the cloud, in the beginning and when you are leaving, you will see some turbulence. Okay, so if the cloud is too thick, probably we have more turbulence, or sometimes for no reason. So that's like everything looks good, but you have some turbulence. That's because you cannot see. If it's a cloud, you can see, but if it's not a cloud, still there can be turbulence. So like small segments of the airspace could have some. So we call that as a airspace hazard. So the point is, let's say this vehicle, the vehicle in front, identifies there is a airspace hazard. If the ground control station knows that there is a turbulent area, that's a different case. Then the ground will warn you. Typically that is the case. If there is a turbulent area, turbulence zone is coming up, then you will the pilot will make an announcement, you are getting into turbulence, get ready, put your seat belts on. So that information actually coming from the ground. But suppose it's not everything can be monitored by ground. So suddenly something happens. So, and if the first drone is detecting this, Okay, before we go further, so I can give another example. A bunch of whole big flock of birds are flying. That also is an obstacle. So somehow the first vehicle may have to detect. It's called detect and avoid. So it should be detect and then also not only that it has to go around, but it may also have to communicate with the other vehicles. So vehicle to vehicle communications are so critical for the safety of people and the vehicles. So this diagram about 5-6 years ago, 4 years ago, I drew, and then this what you call concisely explains why do you need vehicle to vehicle communications and how do you handle this kind of hazards. So that problem is called detect and avoid. So sometimes communication can solve the problem, but sometimes you have to have a lot of sensors. So you need to have sensors to detect all kinds of hazards. Even communications fail, you still be able to autonomously fly. So autonomy, that's why it requires not only communication but a lot of sensors, and then you have to have a ways and means to what you call aggregate this sensory data and figure out what is the extent of this hazard, and then how to plan a reroute, how to reroute. So this is very, it's not an easy problem, and this is very quickly in what I was able to do. We have received so many grants, and I'm personally responsible for 2 standards. One is already released, second is in progress, and then several patents were filed. And again, I'm also personally responsible for a new startup company. And every student who worked in my lab, they got jobs right away. And sometimes it's actually challenging for us to ask students to continue towards masters and PhD because they're getting paid very well. All right, so that's what there's some success stories. So summary is, I call that as a advanced air mobility is adding a new dimension to our lifestyle. That's what I call. So it's like we flew in commercial aircraft, but self-driving cars or autonomous vehicles are something new. Suddenly, instead of a 3-hour commute or journey from home to airport, will cut down to like 20 minutes or 30 minutes. That's a big thing. It's a big thing, provided we all work together, and then if the what I call the dream becomes a reality, and then collaboration is the key. Then you also need to think about community engagement, outreach, education, workforce development. These don't happen in overnight. So this is I call it as a I mean it's a big thing that is happening in the US and other countries, and of course IIT Hyderabad is pioneering this work. A lot of work has been going on, and I believe if you follow the news, IIT Madras also, there is a professor who actually startup company called ePlane. If you haven't seen, just look around and see. I had his name is Satyanarayan, I believe. There's a IIT Madras. There is a person, there's a professor, Satya. His name is Satya. In fact, I asked him to give a webinar in last December. So he has started a company called ePlane, and it's very successful, I believe. Or he's working hard on it. So point is, these are the challenges. Well, I think that's all I have for evening, and tomorrow we'll talk about 2 topics. One is autonomy in airspace and human autonomy teaming. Any questions? This is again just an overview, nothing deeply technical, but it shows what is in the horizon, what is the future of unmanned air transportation. Yeah, like flying cars, right? And but interestingly, the platforms are already there. The vehicle, for example, 5-6 companies were there, and sometimes we see a lot of news in India. So there's a lot of excitement. The point is, what does it take to bring these vehicles in the airspace, put them in the airspace? That is not an easy task. It has to, we have to have regulations. We have to figure out how to handle emergencies, how to handle uh, uh, safety aspects.
But in this case, if any certain object is that, also
It is true, yeah. Safe. It is what we call, there is a risk, there are risks involved, right? So the more we plan ahead, the more we think about how to handle what kind of problems that will arise, then the better it is, basically. In fact, yeah, no, that's fine. In fact, remember I showed you the airspace laboratory. So what I meant that time is, yeah, you can put it on actually. The airspace laboratory is for that. What is a less occupied area, less population is less in that area. So you need to have some sort of a demonstration zone, like the one I showed you. No, video is okay. Yeah. So a lot of things have to be done. Lot of work has to be done. Lot of experiments have to be done, and that's what is happening at least in the US. And I'm sure everybody has to do that. It's not in some places like where regulations are not strict. It's possible to fly drones without having proper regulations, but that's not going to succeed. But you're right. If something happens, what? One accident can spoil the whole show, or all the preparation, and it can make research progress stand still. Yes, so. That's right. Mm-hmm. Yeah. That rule is everywhere. You cannot fly. Suppose you want to fly a drone, okay? You cannot fly within 500 meters. You said, right? For I think Paraji 5 miles. So what we need to do is we need to first inform them. That's a blanket rule, okay? But suppose you design a flight route from airport to some other suburb, like for example, let's say Hyderabad airport to Warangal. Then obviously you need to, the air taxi has to fly from there, right? So, but it is planned. So what happens is, in that case, the routes will be deconflicted beforehand, right? But suppose say you want to fly something, you want to do some experiment, then they won't allow you. But if you take permissions, it's possible actually. That's true. If you have prior permission and if you plan the routes ahead of the time and with approval, and the drone also is like another commercial aircraft. As long as you deconflict the timings, we are okay. But that has to come from the authorizing or aviation authorities, not like private people. So it is true that there is a conflict, but it can be resolved. Hmm. Hmm. That's true. Yeah. I was telling the same. In fact, here is the DFW airport. Obviously, if you have a taxi from the same place, then airport also includes commercial aircraft as well. So, but they deconflict. They plan in such a way that aircraft is taken off from different place. And as you said, as Sir said, it's possible that in some at least for some portions of the flight, you can expect conflicts, but they have to be resolved beforehand. There's a problem because they're still investigating, but it is probably obviously human error. Mm.
where there are military gates and gates.
Yeah, there was a mix-up. Yeah, there was a mix-up of see, military for defense, they're allowed to fly, and they have more flexibility. Yeah. Something happened. Yeah, some. So that's the reason we need to do a lot of testing. So that's the reason we wanted to have a large area for testing. Mm-mm. Mm. No, actually, really speaking, yeah, actually, here we are not really having a different route, the same route actually, but we are showing, yeah, it's both are bidirectional. Yeah, yeah, that's true. Yeah, this actually I personally let this work. Um, that was on the ground. It was not. Yeah, it was actually I didn't go, but it was actually the pilot was the Bell employee was there, but not me. I was there I was there on the ground, not on the helicopter. Any other questions? All right, wonderful. I think this we are done, and tomorrow, yeah.
There are two parts in it. One is if I look from the initial part, like Fuji part, and suppose the undergrad part, if they want to start some aerial communication, what are the few experiments you can suggest so that they can start up their syllabus around their labs? Very clever, right?
Sure, yeah. So one is just to begin with flying, how to fly, how to build it.
They buy some
Small drones and we can fly. Learning.
means if they have a control, they won't have any capability of program.
But it's possible that there are some tools like there's a tool called my students use called PX4 and PX4 and Cesium. PX4 is a PX4, but yeah, PX4 is an autopilot. In fact, whatever you have in the plane is actually can be simulated from the ground on this tool. So PX4 is the same autopilot in software and hardware, software and hardware. So both are exactly
We mostly simulators only, not the
well. We need simulation to fly the drone automatically without remote. So, for example, you can program the drone and send commands to the drone from the lab. We can have our own something called Pix. Or if you buy a drone that has this something called Pix Hawk, that's autopilot. It looks like a small, very small, very lightweight, few grams. That can fly though. That will building drones.
And even they can test it to
Yes, that's
true.
right.
And they can also have some components of drone and start building up drones also. They can have one.
Yes, like yeah, buy the parts and build.
Build them like that.
And then since the first question you were asking is, without remote pilot, we can still fly. We can through this. You can plan a mission on the laptop. For example, if you say I want the drone to fly from here to here, all you need to do is give the direction from the location to what height you want to fly and all that. It will fly exactly as you want.
We can say somewhere they can start.
Yeah. The best thing is go to free space and then.
So these are the few experiments which you can suggest on the UG one. Coming to the PG one, they have to be more serious.
So those are like These are the things. These are the things. These are the results.
So we broadly define that UG program should be a lighter side,
More hands-on, really. More hands-on.
and on the PG part, it should be also more on algorithm.
Like for example, yeah.
privacy.
Collision avoidance is one topic. And conflict management is one topic. Security solutions, sensor data gathering and how to detect.
These are the some opinion of what people think about the UG programs and PG programs. Research directions, you're talking for the last 10 years. The research direction.
Yeah, my favorite topic is autonomy and human autonomy. And tomorrow we'll talk about what is the story of.
So because if you have any
So tomorrow will be the last day. But again, all the technical topics are already covered. Now we are talking about, I call soft topics. There's no equations or anything, just ideas.
okay, thank you, Professor.
Thank
The lecture. And we meet tomorrow for morning 10 o'clock for the. So, can we do it by 9:30 so that we can?
Yeah, in fact, I probably I'll take 1.5 hours, maybe maximum 2 hours.